So the idea in section 4.3 is to start using some of our tools for calculus to understand graphs a little bit better. And an example E here, they give us a lot of information about a graph, although honestly I would find it a little bit easier if I organize this a little bit better. So let's try and do that. Let's start looking at the first derivative. The first derivative is 0 at 3 different points. So let me make my little charts here. I like these little charts, and it helps me to see these on your paper so that I can organize my thoughts while I grade things. You don't have to write them, but I encourage them. In any case, we have points where the derivative is 0, at 2, and at 4. So we have to figure out, well, what's happening with the function at those points. So let's make ourselves, like I said, this little chart here. And I probably should have given myself a little bit more room for the 4. Okay. Well, other way. There we are. Says f prime of x is greater than 0 if x is less than 0 or between 2 and 4. All right, well, let's see. So if x is less than 0, then f prime is greater than 0. So I'll put a little positive there. And x is between 2 and 4, I'll put a little positive there. All right. So what else does that tell us? Well, let's move down here. F prime of x is less than 0 for x between 0 and 2, and x between, well, x greater than 4. So there. Great. Let's also take a look at what happens for the second derivative. So let me get rid of that there. Let's take a look at f double prime. F double prime of x, they don't tell us where it's equal to 0 or not equal to 0. They just say that it's greater than 0 between 1 and 3 and less than 0 to the left of 1 and to the right of 3. So I'm just going to write down a few points here. So we've got x, f, and f double prime. We've got points at 1 and 3. So we're going to do the same thing for those that we did for the first derivative. Now, a lot of times you get some more information about the function. They actually find these values. That would be like a coordinate point if you have the x and the f of x. But looking back here, f double prime of x is greater than 0 when x is between 1 and 3. So I'll put a plus there, and then outside of that we got some minuses. All right, so a lot of information that we can get off of that. Oops, wrong way. And there's our chart. Let's start figuring out what that tells us about our function, because it tells us a lot. It tells us pretty much all we need to know in order to distinguish which of these graphs could actually be that function. So let's start here with the first derivative. Positive, negative, positive, negative. What's that saying about our graph? What's happening to the function to the left of 0? It's increasing, and then decreasing, and then increasing, then decreasing. So if it's increasing, if it's building up to this threshold and then starts coming down, what kind of a point do you think 0 is? What does it have to be? If it's increasing and then starts decreasing, what did you pass when you passed the point that x equals 0? A maximum. All right, so this is, maybe it's a local max, not sure, but it's at least a local max, if not a global max. How about at 2? Now what we got? It's decreasing, then starts increasing. Yeah. It's a minimum, could be a local min, could be a global min, we're not sure. And then finally, at 4, we've got another perhaps local maximum. All right, great. Let's move over to the second derivative. What's the second derivative being negative tell us? What's going on there? Concavity, right? So the second derivative talks about the concavity. Now we're looking at something that's concave down, and then concave up, and then concave down. All right, so lots of information here. By the way, where function changes concavity, do you know what we call that? What's that point called? Yeah, that's our inflection point. In fact, there's two inflection points, right? There's one at 3 and there's one at 1 because the concavity changes at both of these points. So they're both inflection points. So let's take a look at these graphs and try and decide which one seems to be the right one. So we're looking for a function that's increasing until it gets to 0. And then between 0 and 2 it's decreasing. Well, this is increasing until it gets to 0, but it also has a decreasing part here, which I'm kind of unhappy about. Let's keep going. Does it keep following the pattern a little bit? Yeah, it's increasing between 2 and 4. And then at 4 it starts decreasing, but at 6 it starts increasing. So I'm not sure I'm really happy with that one. How about this one? Does that one seem to line up with things pretty well? Increasing to 0, decreasing to 2, that matches. Increasing to 4, decreasing after 4. So that one looks like a pretty good fit. Does it match with our concavity as well? So with our concavity, we got points at 1 and 3. Does this match the concavity? Well, looks like it's concave down until I get to here. And then it's concave up. And then concave down after that as well. So that's looking pretty good. In fact, that looks really good. If we look at the last one fails pretty miserably because to the left of 0 the function's decreasing, not increasing. So this one is our winner. Yay, I like that one. I really think what helps out in these problems is organizing your information here. So I strongly suggest doing these kinds of charts. Not sure I'll require it or not, but it doesn't hurt. How are we looking on this first one? Thumbs up? Yes? All right. Couple, thank you. Let's move on down to the next one. Now some of these get a little bit messy. So occasionally on an exam what I'll do is I'll give you the first or second derivative. But let's go over how to calculate the first derivative. There was something like this on your last exam. In fact, I gave you kind of a choice of 2 problems. That was one of them, or one similar to this was one of them. So let's take a look at example F and work on calculating the first derivative. So our function is f of x is x to the 8th times x minus 2 to the 7th. If we want to find the derivative, then the first thing we've got to do is recognize what rule we're going to have to use. What rule do we have to use to differentiate this? Product rule. Now, if it helps you out, you can write this as a u and a v, and recall that the product rule would look like this. It's going to be u prime v plus v prime u. It feels to me that it would help you out, at least some of you, it would help you out to do that. So let me write it out like that just for practice. U is x to the 8th. What would u prime be? 8x to the 7th. V would be x minus 2 to the 7th. V prime would be 7 times x minus 2 to the 6. And what Faith also recognizes is that you really have to apply the chain rule. So derivative of the outside times the derivative of the inside. But what's the derivative of the inside? 1. So we kind of get a pass on that, which is good. Let's put these two together to find f prime of x. That's going to be u prime times v, so 8x to the 7th times x minus 2 to the 7th, plus v prime times u. Now, just for convenience, well, let's see, I'll just write it like that. 7 times x minus 2 to the 6th times x to the 8th. Be careful with your algebra here. There was a few people that wanted to distribute this into the parentheses, distribute that into the parentheses. You can't. If you keep in mind your order of operations, kind of that old little ditty about please excuse my dear Aunt Sally, which isn't really all that great, but parentheses have to be done before exponents and multiplication. So you can't multiply before you take care of this power. So you have to do something with that before you distribute. Instead of distributing, though, let's factor out the greatest common factor. The GCF here. What's that going to be? What's common to both of these terms? Let's start out with the x's. How many are common to both terms? 7 of them. And then we're going to do the same thing with the x minus 2's. So I've got x to the 7th times how many x minus 2's? Good. That's what's in common to both of these. All right, so that's what I'm going to factor out. That's going to be x to the 7th times x minus 2 to the 6th. And just for ease of visual sight, I'm going to put a bracket here. If I take out x to the 7th and 6 of these, what's left behind from that first term? All right, there's an x minus 2 to the first power, which I'm not going to write to the first power. What else is left? Yeah, there's an 8 there that's left. Plus, well, I'm going to take out a bunch of stuff from here. It's certainly going to leave behind a 7. Anything else? Yeah, one of the x's. Let me pause here. I mean, they pay me to teach. They don't pay me just to, sit up here and talk. So let me ask you, are you comfortable with this? This is not the only time you're going to see this. It's not the last time you're going to see this. So are you comfortable with that factorization? Because that's what really has to happen in order for you to finish solving this in any reasonable amount of time. Let's keep going. X is 7th, x minus 2 to the 6th. If I distribute this, what would I get? 8x minus 16. And 8x plus 7x is going to give me 15x minus 16. I want to know where that's equal to 0. Now that it's nice and neatly factored like this, this part of it isn't so bad. One last go at this. Are you okay with this factorization? And this is just something that we just have to do. All right, so we've got product of this times this equals 0. One of these things has to be 0. Either x equals 0 or what else? X equals 2 or 15x minus 16 equals 0, meaning x equals 16 over 15. What do these values of x represent? Yeah, those are your critical points. So we'll have to turn our attention to those in just a little bit. Now, differentiating this again becomes a little bit more of a pain. You've got to be creative in applying the product rule. You've got to group one of these things together, either this pair or this pair, and treat that as a function and then apply the product rule to something. You'll have a nested product rule. It becomes kind of a mess. So out of kindness, I've got this here, right there. So I've given you the second derivative. That's what this is. You're applying the differential operator to this twice. You're squaring it. So we end up with this. That's a nice big help because it means we don't have to set that equal to 0, or it means we don't have to solve that for ourselves. Does leave us a little bit of a pain right here. Now, the question that's being asked in this is, what does the second derivative tell us about f of x? Let me get to that as we look at our critical points. And we'll talk about something called the second derivative test. What you'd want to do with your critical points is help set up a little chart here so we can look at the graph. So let's do that. X, F, F prime, 0, 2, and 16 over 15. So we know the function is 0 at these points. That's fine. But we don't know the nature of these points. And that leaves me with a lot of work to do. So just try and decide if these are minimums or maximums or what's going on with these particular points. So in order to do that, we can test some points. We know the derivative is 0 here, so they're critical points, but are they minimums or are they maximums? Well, let's plug this function into our calculator and see if we can't find out. Now what we're doing by deciding how the signs change around the derivative is applying what's called the first derivative test. We did that with our first example. We went from positive to negative. Oh, that's a max. Negative to positive, that's a min. This is the first derivative test. We're going to introduce the second derivative test in just a minute. Let's put in this function. And by the function, I actually mean the derivative. 8x to the 7th. And then, let's see, x minus 2. Actually, no, I copied the wrong one. How about I do x to the 7th. X minus 2 to the 6th. And finally, 15x minus 16. Bam. Okay, so now I get to test some points here. What I have to do is I have to test points in the appropriate intervals. Hopefully your window settings are correct. If you hit the second key, then the window key. Hopefully your window settings are independent set to ask, dependent set to auto. When you go over to your table function, let's delete those values. I need some points that are kind of in between these places. So what would be some points that I can test to the left of 0, between 0 and 2, between 2 and... actually, can anyone see a mistake that I made? Yeah, the order is all screwed up. I'd have a hard time trying to find something between these 2 points as written. So, 16 over 15 and 2. It might help to figure out a decimal value for 16 over 15. I'm thinking 1 point, let's see, 16 over 15. Yeah, 1.06. So, yeah, 1.06, that's a decent enough decimal value that we can figure out something here. So I need some test points. What would be some good test points? So left of 0, -1. Between these two, you can use 1. That's less than that. And then how about between these two? What am I going to use? 1.5 and maybe 3. Those would be some good test values. Bless you. So let's use those test values. -1, 1, 1.5, and 3. Wow. Some pretty big numbers, but I don't really care about the numbers themselves. What am I really interested in knowing here from this chart? If they're positive or negative. Yeah, positive or negative. That's all I need. So it was plus, minus, plus, plus. All right. So let's write those down. Plus, minus, plus, plus. So see what that tells us about our function. It's increasing, then decreasing, then increasing, and increasing again. So try and go through and label what you think. Basically, we're using the first derivative test to decide, are these minimums or are they maximums or neither? Valerie, what's going on at 0? All right, we got a maximum point, and then Nicholas, how about a 16 over 15? Minimum. Nice. How about a volunteer for what's this saying about x equal 2? Yeah, basically it's neither, however you want to say it. But what looks like could be going on here would be a inflection point. And we can know that when we look at the second derivative. And the second derivative, fortunately, is given to us. So kind of an ugly expression. That's okay. But there's the second derivative test. Second derivative, yeah, might help if I concentrate. Second derivative test. It's going to look like this. And before I discuss the second derivative test, let's see if we can't try and make sense out of it. There and here. Suppose you have a critical point on a function. And a lot of times it's going to look like one of these two things. What kind of a shape of the graph do you see at this point? And by that, I'm thinking concave up or concave down. Concave up, and then concave down. So if you knew that these were critical points, and the shape of the function was concave up there, then this has to be a minimum. Minimum. Or if you knew that this was a critical point and the shape of the function was concave down, what kind of a point does that have to be? A maximum. So if you have a critical point of a function, if C is a critical point, and f double prime of C is greater than 0, then what has to be true about C? Well, then x equals C is a minimum. And f double prime of C is less than 0, then x equals C is a maximum. So sometimes it's a shorter way to decide if something is a minimum or maximum, because a lot of times once you do this, once you find these critical points, you don't know if they're minimums or maximums until you start looking at the graph. So That's the second derivative test. Does it work for us here? Well, let's just kind of do a quick little test at x equals 0. And yeah, I think x equals 0. We might not get any information on that. If f double prime of c equals 0, then the second derivative test gives no information. It's inconclusive. Okay. Let's take a look at the second derivative here. For us, that's given f double prime of x. And let me just kind of zoom in on it for a second here. Always do that. 14 times x minus 2 to the 5th times x to the 6th times this ugly looking quadratic. So you can see why I gave that to you. Getting that, you know, through some algebra and some calculus would be kind of a grind. So if you wanted to figure out are these minimums and maximums, you could actually just plug in some test points. Actually, not test points. You can plug in these values into the function, and as long as you get something other than 0, then you know if it's a minimum or maximum based on the second derivative test. I'm not sure I want to try and plug in 16 over 15 into this function by hand. I think I might do a hard pass on that one. Is it worth it to you to take the time to plug in this function just to evaluate the function at 16 over 15? What should happen at 16 over 15? Should I get something less than 0 or greater than 0? So this is a minimum point at which, if that's the case, then the second derivative should be of what sign? If you have a concave up shape. Second derivative there should be positive or negative? Positive. So f double prime of this should be greater than 0. You ever seen this triangle of dots? Mathematically, it means therefore. X equals 16 over 15 is a minimum. There's a couple mystery functions that I have too. There's links for those on D2L if you want to kind of take a look at those there, follow along. But they're doing the same kind of thing here. They're giving you some information about the function, and we're going to see if we can't graph them. Let's do one of those together. We'll start with the first one. And here's some of the information that you're given. Now, I forget whose paper it was. When I grade exams, I don't look at the names until I'm all done and have to total up points. So I feel I'm more objective there. But somebody did something a little bit really cool on one of the problems, and that is they looked at the domain and said, oh, well, the domain has to be 0 to infinity. And I'm like, oh. So I gave a couple bonus points for that person. In any case, you should always start by looking at the domain. The domain of this function is -2 to 2. So it's just here. That's it. That's as far as this function is defined. Let's try and make ourselves a little chart based on some more of this information. F prime of x is greater than 0 between -square root of 2 and square root of 2. Okay. So it looks like square root of 2 and 2 are some critical points. Let's see what's going on there. Draw ourselves our little chart. X, F, F prime, negative square root of 2, positive square root of 2. Now it's not really saying what's happening at these functions or at these points, but it is telling me what's happening with the function between these 2 points. And that is the derivative is greater than 0 between those 2 points. And outside those 2 points, the derivative is less than 0. So that gives us some information about our function. What's happening to the function to the left of square root of 2? Decreasing, then increasing, then decreasing. Faith, what's that mean is going on at the negative square root of 2? Yeah, that's a minimum point. And square root of 2 is a maximum point. Nice. So a couple things that we knocked off here. There's a little bit more information we get from this chart here. And that is the second derivative is less than 0 on the interval 0 to 2 and greater than 0 on the interval negative 2 to 0. So looks like things are happening around 0, x, f, and f double prime. So to the left of 0, the first derivative, or the second derivative was positive, and here the second derivative is negative. Zaid, what's happening with the function if the second derivative is positive? What's its shape there?
Goes up.
Concave up, good, and then concave down. Thank you. Anika, how about at 0? What does it say about 0 if the second derivative is going from positive to negative? Yeah, it's an inflection point. Well done. Thank you. Now start trying to form a little picture in your mind while I look over at the link. So here's mystery function 1. There's all the attributes. So the graph has a point corresponding to negative 2 and 0. This is also, and I'm not sure if I mentioned this in the description or not, this is an odd function. Do you remember what it means to be an odd function? It means 0 is kind of like this line of symmetry for your graph. So the line that passes through the origin and passes through this other point has to have a mirror image on the other side. So if it's an odd function, then we're going to get a point on the other side of the origin. Where? Yeah, at positive 2. And in fact, there's a couple other points that are drawn for us on our graph right here. What was happening between square root of 2 and negative square root of 2 and square root of 2? Well, the function was increasing. So it's going to look like that. Where was it decreasing? Oh, right there. Okay. Does the function have an inflection point? Yeah, where was it? It was at the origin. So, great. 0 is an inflection point. Looking good there. I think we got all of it that we can off of this in terms of our graph. So we can connect the dots here. Function looks like this. I think it's the square root of 4 minus x squared, if I remember right. But there is an inflection point. You've got a max here, you've got a min here, and that's it. There is another one of these mystery functions that I'll have us do later, work on them in groups. But this is the kind of information that I want to see you use when you're working with these graphs. So, comments or thoughts on that example G? How did I fill in the first what?
The first table were negative root 2 and
From this information right here, and it doesn't show up too well on your thing, but that's f prime of x is greater than 0 between negative square root of 2 and square root of 2. So that's where I got these points. And then it's less than 0 in the intervals outside of that. That's the second line there. Does that help out? Okay. Appreciate the question. Anything else? Okay, so let's put part 2 to bed.